This is the first of 3 videos from Chapter 11, which is about liquids, solids, and really primarily about intermolecular forces. And this first of 3 videos concentrates on the types of intermolecular forces. First, to clarify what intermolecular forces are, is those are the forces of attraction between molecules. Okay, so if we're looking at a water molecule, a chemical bond is actually an attractive force, but chemical bonds are internal or intramolecular bonds. What we're talking about in this unit are intermolecular bonds. So that would be the forces of attraction between 2 different water molecules, for example. Intermolecular forces are important for a variety of reasons. They affect a lot of physical properties of the compound, which is the subject of the second video. But just as a brief introduction, solid materials have very strong intermolecular forces, and that's why the atoms or molecules of a solid are so tightly packed. Liquid materials have somewhat weaker intermolecular forces than solids, and that is exactly why the molecules have some space between them. And gases have weak to no intermolecular forces or forces of attraction between molecules, and that's why there's so much space between them. All right, so just to kind of summarize the results of the different strengths of intermolecular forces, I'm going to highlight a couple things in this chart below. Those are my dogs. I have 2 large standard poodles, and they will definitely make entrances throughout my lectures. I think most of these properties you've probably learned since middle school, if not before, but make sure you're real familiar with them. Just there's usually a couple of trivial multiple choice questions about them. But if we have a gas, the intermolecular forces are weak. And remember the basic properties of a gas. They assume the shape and volume of any container they're put into. They're very easily compressed. Liquids, on the other hand, they have moderate intermolecular forces. So they are closer together than a gas, not as close together as a solid. Even though they do have some space between the molecules, they're virtually incompressible, so that trips some people up. Try to think of squishing a glass of water to a smaller volume. You're not going to be able to do it. Okay, and then finally, solids have the strongest intermolecular forces, completely incompressible, very high density. So really what I want to emphasize here is remember not only all the properties of solids, liquids, and gases, but that they are in the state of matter they're in because of the intermolecular forces that the individual molecules or atoms experience. All right, so this is still one of the kind of introductory slides, and the third lecture in Chapter 11 will go over solids in more detail, but just kind of to introduce. There are 2 basic categories of solids. There are crystalline solids, which are the beautiful ones to look at. Salt and diamonds are the examples given here. And there is something called amorphous solids. And I always think that word itself sounds like what amorphous means, which is just kind of squishy. I really shouldn't say squishy because they can be hard, but no particular shape. So plastics would be amorphous, okay? Crystallines, if you see a beautiful solid, then that's a crystalline. Thinking about liquids on a molecular level is kind of interesting. The intermolecular forces, as I said before, are moderate, and so there is some small amount of space in between the molecules. It's not enough space to make liquids compressible at all, okay? So they're considered incompressible. However, it is enough space for these molecules to slide past one another. And that ability to move or to slide past one another is why liquids are pourable. So you have a glass of water and you want to pour it into a different glass. You can do that because those small amount of spaces in between molecules, and you cannot do that with a solid, for example, because the molecules of a solid are so tightly packed they cannot slide past one another. So solids don't flow. And of course gases, later on when we get into the chapter about gases, and you may already know about them, they have very weak intermolecular forces, and it's pretty safe to make the assumption they have zero intermolecular forces. That's why all gases can be mixed completely. They don't repel or attract each other, so they don't really care about what other gas they may be mixed with. All right, I'm going to go just skip over this one. I feel like I'm being really redundant at this point. All right, so all intermolecular attractions are based on electrostatic forces. What's an electrostatic force? It's simply a force between two charges. It doesn't have to be a full charge like an ion. It could be partial charges. Any type of charge development whatsoever sets up electrostatic forces. And so we will learn about three basic types of intermolecular attractions, and all three of those are based on these attractive forces, attractive electrostatic forces. All right, so the three basic types of intermolecular forces we're going to learn about are, one, London dispersion forces. Those are the weakest forces, okay? Now we're getting down to the meat and potatoes of this lecture. This is stuff you really need to know. The second type of intermolecular force of moderate strength is called dipole-dipole. And the strongest type of intermolecular force are hydrogen bonds. Now, it's unfortunate that they named this intermolecular attraction with the word bond, because I just tried to emphasize very much so in the first slide, the intermolecular forces are not bonds in the classic sense. They're many, many times weaker than an intramolecular bond, like a covalent bond or ionic bond between atoms. But anyway, hydrogen bonds are the strongest type of intermolecular force. All right, so we'll go over each of those three in a little bit more detail. London dispersion forces are present in all molecules. That's one of the things, don't get tricked into that. They are the weakest. There are some molecules that only have London dispersion, but it's important to realize that every single molecule and atom has these London dispersion forces. What are those? They are temporary or instantaneous attractions. How do they come about? Well, at any point in time, we know the electrons around the nucleus. We're not sure how they move, but we know they are moving. And so there are times where the electrons will be kind of congregated in maybe one portion of an atom, and that'll set up an instantaneous and temporary separation of charge. So on the side of the atom where the electrons are congregated, we'll adopt a partial negative charge, and the side of the atom that is deficient in electrons will adopt a partial positive charge. That is set up for electrostatic attractions and repulsions, okay? Because this atom with its temporary dipole now induces or causes a temporary dipole in the atoms around it. It's kind of like a chain reaction. But anyway, very short-lived, very weak, but it is in fact does serve as an attractive intermolecular force. All right, again, London dispersion forces are present in all molecules. You'll sometimes a lot of people just call these dispersion forces, so I don't want that to throw you off. So what makes some molecules have stronger London dispersion forces than other? There are a couple of factors that determine the strength of it. Probably the most important one is called the polarizability of an atom or a molecule. And basically what that means is how easily the electrons can move in that atom or molecule, okay? So the more tightly electrons are held, the closer they're held to a nucleus, the less polarizable they'll be, okay? So what that means basically is the larger the molecule, the farther out its electrons are going to be, the farther away the valence electrons will be from the nucleus, and therefore the easier it is to distort those electrons or to move them around. That's called polarizability. If you can distort an electron cloud and move it around, then it's polarizable. That leads to higher London dispersion forces. Okay? Bottom line, larger the molecule, stronger the London dispersion attraction. All right, so this graph gives you a visual of the effect of the size of a molecule, and we're calling it molar mass here. Okay, obviously the larger a molecule is, the higher its molar mass, versus boiling point. Why am I talking about boiling point? Well, this is a really important concept. What happens when you boil something or you melt something? You haven't broken any internal bonds, okay? You haven't changed the chemical makeup of the compound. What you've done when you melted or boil something, you've just loosened up the intermolecular attractions between molecules. So the boiling point, and again, our second lecture will go over this in more detail, but the boiling point is a measure of the strength of the intermolecular forces. Okay, the higher the intermolecular attractions are, the higher the boiling point. So let's look at it for a minute. Along the y-axis, we've got boiling point of the compounds, and along the x-axis, we have molar mass of the compound. So what's the relationship between boiling point and molar mass? Obviously, as molar mass goes up, boiling point also goes up. They're directly related, okay? And that's because of the London dispersion forces. I said in the last slide that the higher the molar mass is, the stronger the intermolecular forces, and therefore the higher the boiling point. If that's confusing to you, you might want to listen to the last two slides again and jot down that summary. It's really important to understand. All right, so the size of a molecule affects the strength of the London dispersion forces. What else affects it? Well, if you have a molecule that's more linear, more stretched out, more surface area, okay, then it's going to have stronger London dispersion forces, okay? If it's bulkier, more compact, more like side chains and things, you will have weaker London dispersion forces. Makes kind of sense, right? If you have something long and stretched out, it's easy to kind of lay next to something else that's long and stretched out, get entangled, and kind of harder to tear them apart, okay? So the linear molecules will have higher boiling points, higher melting points, okay, because they have higher London dispersion forces. All right, so now we're going on to the moderate strength intermolecular forces. These are called dipole-dipole. So whereas London dispersion forces were a result of temporary electrostatic attractions, dipole-dipole intermolecular forces are permanent electrostatic attractions. Those occur between molecules that have permanent partial positive and negative charges, permanent separation of charges. So if you remember from the first semester of chemistry, that would mean dipole-dipole attractions occur between polar molecules, because it's the polar molecules that have this separation of partial charges. Alrighty, so as a summary, the more polar a molecule is, and how do we measure polar? It's measured by something called the dipole moment. That's what you'll see in tables. Dipole moment, sometimes they call this, it's actually called a mu symbol. Looks like a U with a tail. So the higher the dipole moment is, the more polar a compound is. And what effect do you expect more polar to have on boiling point? You see, as dipole increases, so does boiling point. Very good correlation. And the sizes, the molar masses, are about comparable for all of these. And there go my dogs again. All right, so the third and last type of intermolecular force that I'm going to go over is hydrogen bonding. Hydrogen bonding is the strongest of the three we've talked about. Hydrogen bonding is a type of dipole-dipole, okay? But it's a particularly strong type of dipole-dipole. Hydrogen bonding can only occur when there is a hydrogen atom that is directly bonded to either a fluorine, an oxygen, or a nitrogen. I'm going to have to stop him. I always like to say, just to help you remember what types of compounds can hydrogen bond, I say hydrogen bonding is fun, isn't it? Get it? Like fun, have fun, but really with an O, fun. Anyway, so ammonia can hydrogen bond, water can hydrogen bond, hydrogen fluoride can hydrogen bond. Okay, but only hydrogens directly attached to one of these three atoms can hydrogen bond. The strong attraction is just something to do with hydrogen being such a small atom. It ends up contributing to an extra strong dipole that forms. So anyway, keep a lookout for hydrogen bonding because that's the strongest type. So anything that can hydrogen bond has an exceptionally high boiling point. So water, if you think about water, only has a molar mass of 18 grams per mole. It should be a gas. Anything else with that small of a molar mass would definitely be a gas. But water's a liquid, and that's because the intermolecular attractions between molecules are so darn strong due to the hydrogen bonding. So that makes it a liquid. This is just a pretty picture. All right. Alrighty, so just give you some quantitative data for the effect of hydrogen bonding. So if we go, let's look at this bottom line. All right, so we start with nonpolar methane. It just has carbon and hydrogen bonds. It is a gas. It is already boiled way down at almost minus 200 degrees Celsius. If you go, carbon is, let's see, row 4A on the periodic table, okay? If you go down, then we have on the periodic table silicon, germanium, okay? So if you go down, obviously the mass of these is increasing, and you would expect the boiling point as the mass increases to go up, and it does. No surprises there, okay? And that's true of the other group A's. Look what happens, though, when you get to nitrogen, fluorine, and oxygen, okay? So nitrogen is in group 5A, oxygen is 6A, and fluorine is 7A, okay? When you get to those, look at these three, ammonia, hydrogen fluoride, and water, should be way down here someplace at their boiling point, but instead they have really high boiling points, and that's because these three can hydrogen bond. So their intermolecular forces are exceptionally strong, and this type of behavior is exactly why scientists discovered hydrogen bonding. They were just so far away from what was expected for their boiling points. All right, so here's an example question for you. if I would say identify the type of intermolecular force for each of these and tell me which one has the stronger intermolecular force. So in order to do this properly, you're going to have to remember, you're going to have to harken back to the first semester of chemistry where you learned about molecular shape and molecular polarity with symmetry. So if you're not comfortable with that, you're going to have to review a little bit, okay? So, for example, let's look at boron tribromide. Boron-bromine bonds are polar. So you might think, okay, it's got a dipole, so does it have dipole-dipole? Well, no. In order for this molecule to experience dipole-dipole interactions, it would have to have net polarity. And as it turns out, because boron tribromide is completely symmetric, that all of these dipoles cancel each other out. There is no net dipole. Therefore, it is nonpolar overall. And so any nonpolar molecule only has London dispersion forces. Okay? Same holds true for either one of these. So if they only have London dispersion forces, then which of them would be stronger? If you're talking about London dispersion, what is a factor that makes one molecule a stronger London dispersion than another? It's the molar mass. So which of these has a higher molar mass? The one containing bromine. Okay, so that's the stronger intermolecular forces in question A. Let's look at question B. Both of these molecules are polar. Okay, they both have a polar molecule. This one has oxygen, this one has chlorine. They're not completely symmetric, so they have a net dipole. So we would expect them both to have dipole-dipole attractions. However, there's something special. This is ethanol. That's actually the alcohol they put in drinking alcohol. There's something special about ethanol that ethylene chloride doesn't have. Hopefully it has popped into your mind. Ethanol can hydrogen bond. Remember, you can only hydrogen bond when you have a hydrogen directly bonded to a fluorine, oxygen, or nitrogen. Therefore, ethanol has stronger intermolecular forces and should have a higher boiling point. All right, so one of the things we haven't really gone over, but I want you to be aware of, and that is, even though 90% of the time we're going to be talking about the three intermolecular forces I've introduced, I want you to be aware of ion-dipole attractions. That comes up, that's more important in chapter 12, the next chapter. But the bottom line is, you can have attractions between something with a dipole, like let's say water, and an individual ion. So let's say we had sodium chloride and we dissolved it in water. So we had a saltwater solution, okay? What's going on between the ions and the water molecules is also an intermolecular force, okay? Remember, inter just means between. So technically, that's an intermolecular force. And because the ions have fully developed charges, it turns out that the strength of the attraction of an ion dipole is actually stronger even than hydrogen bonding, okay? So if at the end of the semester in your ACAS test, they try to trick you and say, what's the strongest intermolecular force? I just want you to be aware that ion dipole is technically an intermolecular attraction and is stronger than even hydrogen bonding. Here's a summary page for you. Just kind of put everything in one place if you want to jot it down. It's a good slide for studying. I think I'm just going to pause and let you listen to my dog bark and read this. There's nothing new here. It's just a summary. Okay, and it is the last slide. Another summary slide. It shows you a pictorial of all the different types of intermolecular forces we've talked about. That's it for the first lecture. You can make sure that you take the quiz associated with this lecture located in Learning Catalytics. And I will see you at the second lecture, which is about how intermolecular forces affect properties of molecules.